means there is no single search algorithm that performs better than any other algorithm on all data sets. So no algorithm is definitely much better than others. For example, I have a random search algorithm. This random search algorithm, in some cases, may not perform worse than those advanced search algorithms. So remember this. And that means, first, you don't have to depend on a specific algorithm. You may want to change your algorithm according to the nature of your problem. The second thing is, you have to understand the nature of algorithm. For example, understand the landscape first, then choose your algorithm. So don't fix your algorithm and change it and go there directly, but explore the landscape before you choose your algorithm. And here I listed many famous heuristic search algorithms. The first one is called gradient-based search. And this is also called hill climbing. Let me show you what it means. So you randomly put some candidate solutions, put some values. I mean, you have two parameters which can be comprised as a vector, and you randomly put vectors, put some points here. And for each vector, each point, you search along the gradient. So at every location, it has a gradient. Suppose it's differentiable, it has a gradient. Then you follow the gradient to the bottom. That means hill climbing or gradient-based search, right? So in this case, for example, if you put a point here, you'll be trapped here in the local minimum. But if you're so lucky that you put a point here, then you're going to find the global minimum. And you put, if you throw as many points as possible, then according to the law of large numbers, you are going to get this minimum, right? So that's a basic heuristic search algorithm you can use. And based on that, people have developed a lot of such algorithms, such as genetic algorithm, which I introduced in last year, or maybe the beginning of this year. Simulated annealing. Simulated annealing means that there is an environmental temperature. When the temperature is high, you may go, for example, you may go backward. You may, for example, if you use gradient, you have to go this way. But when the temperature is high, you may go up. So that gives you some ability to jump the hill. Let me say that again. If you are here, according to the gradient, you have to go down. But when the environmental temperature is very high, you may go upstream. And in the beginning of the simulated annealing algorithm, the temperature is very high. So the points are going randomly. And after a while, the temperature is lower. It has been lowered. So all of them are going according to the gradient. And that's a simulated annealing search. And taboo search, which you have already learned in the optimization class. And I want to introduce this particle swarm because it's less known, less famous than all of these. This particle swarm search is developed in 1990s. And I want to show you a video to let you understand what it is. So let me first show you a video. This is particle swarm. These red dots represent the current optimal. So for every iteration, there are some, the yellow dots are representing the current solutions, the current search space. You may not understand what it is. So let me introduce you first. For particle swarm, you have a swarm of particles or points. And each point has a velocity and a position. And all the points are moving. In the beginning of the search, all the points are randomly given out. So they are all assigned a random speed and a random location. And then you can evaluate all those the objective functions of these points. And you are going to get which one is the best. Now, in the next iteration, all other points will change their speed to follow this leading particle. So if they're here, if the best one is here, all those particles will change their speed toward this leading particle. And that repeats. So if somebody here, if you think these 4 dots are representing the birds, then it will be easier to understand. So you have a leading bird. In every iteration, you have a leading bird, and all other birds will try to go toward the leading bird. So they change their velocities.
So the direction you mean, or the speed? You mean the
speed is the speed is a vector, right?
Vector,
the direction of their speed. So, and this search algorithm was initially developed for studying the social activities. It was not developed for searching any calibration parameters, but it's later used to search all kinds of things. This is easy to implement, so it has become popular. Okay, and there are a lot of other heuristic search algorithms. Now, after calibrating the capacity, we may want to calibrate the route choice. And we also have 2 steps, global calibration and fine-tuning. I don't want to emphasize too much on this because you are going to use similar procedures, very similar procedures. Then the 3rd step is called system performance calibration. In this step, you are going to get a systematic or system-wide performance. And that will be your final goal. This table is created by Wisconsin DOT in 2002. And this is recommended by FHWA. So let me analyze some of them to you. For example, this is the criteria. This is the target. And you don't want your model to 100% fit the data, right? Because that will take infinity amount of time. It's impossible. So how good is good enough? This is the criteria. For example, if a link that is having more than 2,700 vehicles per hour, then the target of your calibration should be within 400 vehicles per hour. The difference will be within 400 vehicles per hour. Then this criteria can fit for 50% of the cases. In another word, 85% of the links are having difference within 400 vehicles per hour. If the target flow is 2,700. Do you understand this? Similarly, for 95% of the case, the GH should be less than 5. So you check these criteria one by one. Then you can say, okay, now my model is already calibrated. This is called system performance calibration. This is the last step. And here is an example of our previously calibrated CCMPO model, Cheatham County, Vermont. And they use the figure to show it. So they use colors and they use different width to represent different absolute difference. And they use the color to represent the relative difference. And in this way, you can visually see that the system's performance, the calibrated system performance. So this is a tool you may want to use. Okay, good. Now homework 10. Homework 10 is not about calibration. It's still about the last lecture, because I think last lecture is difficult for you to understand. So I first let you understand the concepts, and this time I want you to understand the package, understand the batch files, And you may want to start with this readme.txt. This file will show you how to run it. And running it is easy, but try to understand it. I mean, you may want to submit necessary screenshots. Only screenshots, no narrations. And this part will be tested in the midterm, which is 7 days from today. Any question about this? No? Here are some notices. First thing is about homework 9, which is about 8 or 9. Homework 9. Oh, I already forgot. Maybe it's not homework 9. It's about the vSIM DTA. Because some of you cannot run vSIM, then so I postponed this homework. And now it's due before Thursday's class. I mean, before Thursday. And Thursday's class will be a review. And I will be very glad to answer your questions. Please send me your questions before the class so I can prepare ahead, so I will not mislead you. And for the class project, please prepare the topic. If you don't have any topic, we can just calibrate the transients model. So if you don't have any topic, I will assign you a project of our group. If you have your own topic, just let me know, please. And in the midterm, I want to emphasize, you don't have to print out all the slides and bring it here. Although it's open book, you don't have to do that, because I'm not going to test your memory. You don't need to, I'm not going to test your memory. I'm not going to test your calculation skill. So you may want to bring your calculator, but you won't be able to use it unless your calculation is too weak. Right? But I want to test those must-know concepts. For example, capacity is, or volume is. These things should already exist in your brain. So 80% of them are for must-know concepts. And the other 20% of them are for problem-solving abilities. And this part you won't be able to prepare, right? So I have already given to you a lot of slides. And for those slides, I don't want you to print every page because that would be a waste of paper. And I ask you to send me the PDF files because I want to save paper. Okay, and that's the only reason I want you to send me electronic files. So I don't want you to print them because that would be a waste of paper. So let's do our contribution to the earth. I'm serious. Okay. So now it's the end of lecture. Please prepare your questions. Thank you.